Hello, my name is Samir Gupta. I am the Customer Marketing Manager for Industrial Controls and Automation within the Embedded Group at AMD. I am here today to talk to you about virtualization and its application in industrial controls and automation. Virtualization is a part of AMD 1.0. AMD is a term used to describe the various open standards-based technologies used to help fulfill the increasing security and reliability needs of embedded solutions, and it includes AMD virtualization and security. AMD supports choices in the marketplace with 1.0, and open standards-based management tools and technology provide the essential management features businesses need today to easily and flexibly support embedded systems. Proprietary management solutions can overload systems with non-essential features, lock organizations into specific vendor solutions, and increase management costs and eliminate flexibility. 1.0 is based solely on open standards to enable manageability, virtualization, and security with features that don't lock solutions into a single proprietary technology. By deploying systems that support 1.0, OEMs can now simplify the embedded system management process and manage a mixed environment in a consistent manner, helping to reduce complexity, simplify administrative tasks, and contribute to overall lower system cost. Today, we will be primarily talking about virtualization's part of 1.0. But first, I would like to give a brief introduction to the other parts of Dash as it relates to industrial control and automation applications. Many industrial control applications are becoming more networked through standard IP-based networks, and the rise in attacks on these industrial control applications is driving increased need for protection of confidential recipes or process information and safety-sensitive control commands across the network. AMD promotes open, industry-standard security solutions for embedded applications. Trusted computing is a category of technology developed and promoted by the Trusted Computing Group, of which AMD is a member of. The Trusted Computing Group, TCG, was formed to develop, define, and promote open and vendor-neutral industry standards for trusted computing building blocks and software interfaces across multiple platforms. Trusted computing is the industry's answer to growing security problems and is based in a hardware root of trust, helping to make embedded systems, applications, and networks more secure. Through the implementation of an onboard trusted platform module, an embedded platform can benefit from authentication, data protection or encryption, identity and access management, password management, network access control, and layered security. Remotely managed enterprise servers and office computers for system health monitoring and maintenance have been a critical function within the IT toolbox for many years. But those very same capabilities have largely eluded systems on the factory floor because of the high cost of existing solutions, and implementing them is considered overly resource intensive in both cost and time. Factories have grown into highly dispersed networks of interface, control, and data acquisition systems. Along with that growth, the cost of deploying and administering and the maintenance of those systems has increased. To manage these costs while at the same time increase reliability and uptime, automation engineers have begun to investigate in remote management techniques designed to simplify deployments and to reduce the costs associated with the administration and maintenance of those systems. Remote management can help reduce factory downtime through service alerts and remote diagnostics, help improve security through the ease of deployment, track software updates, and help reduce power by powering down systems when they're not needed. The gold standard for remote system management is a set of specifications known as Dash. Dash is very robust, an attribute that makes it appealing for enterprise computing infrastructure. Companies today use Dash for system monitoring, asset management, and ease of deployment of software upgrades and patches, among other benefits. Because it is built around open standards, Dash helps lower total cost of ownership. But the over-design and complexity of Dash solutions targeted at enterprise applications can add costs and has discouraged its adoption in many embedded applications. AMD has created an implementation of Dash specifically for embedded platforms that removes the bloat of the cost for a Dash compliant system. Moving on to the topic of today's webinar, virtualization. In the past, many embedded applications have utilized separate processing platforms in a system for security, performance, and reliability reasons. By running applications on a completely separate platform, applications could be fully isolated from one another. This would help prevent external or low-priority processes from accessing critical or sensitive data, as well as prevent other external or lower-priority processes from interfering with real-time or reliable operations of a critical subsystem. Through virtualization, developers can now implement completely isolated applications and operating system functions on a single processing platform, enabling less complex, lower power, and lower cost system implementations. AMD embedded SoCs and APUs both support AMD V technology. AMD V technology is a set of unique, on-chip features that help AMD processor-based platforms run multiple operating systems and applications on a single platform by improving the efficiency of virtualization software. There are a number of underlying factors that are driving the trend towards virtualization in industrial control applications. The need for more automation on the factory floor is fueling the Internet of Things, where billions of devices are seamlessly connected to one another with real-time performance. With increasing machine-to-machine connectivity, more workloads are now being consolidated into a single device. The challenge facing factory automation engineers here is how to share and manage the data securely and reliably on the network or the cloud. Recent years has given rise to performance demands being placed on industrial control systems to support a variety of user interface, data visualization, and data processing needs. This has driven the need for both low power and high performance systems to do more, and the requirement for multi-core architectures to perform multiple functions at the same time. In turn, to enable designers to reuse existing hardware and software across a product portfolio and realize significant development and support cost savings, system scalability is being enabled through a single architectural platform that can scale in price, power, and performance. Finally, rising costs associated with deploying multiple systems across the plant floor is driving the need to better integrate more functionality on a single platform to reduce deployment, training, and maintenance costs. As a consequence, to increase connectivity and computational performance needs and the desire to integrate more cost-effective platforms on the plant floor, more customers are turning to x86-based architectures like the AMD G-Series APU and SoCs versus traditional microcontroller-based solutions to leverage features like virtualization to help meet their connectivity, security, performance, scalability, and integration needs. Before we discuss the specific virtualization features implemented in the AMD SoCs and APUs and the example use cases for virtualization for IC&A applications, it is important to review the types of hypervisors available today. A hypervisor is a virtual machine monitor or VMM, which allows multiple operating systems to run concurrently on a host computer. Support for virtualization and hypervisor technologies have long been used extensively in the IT and server market space and are now making their way into industrial control type applications to enable multiple operating systems to be run safely and securely on a common hardware platform. The two commonly supported hypervisors in embedded system designs today are native or bare metal hypervisors and hosted hypervisors. Type 1, referred to as native or bare metal, runs directly on the host hardware to control hardware and manage guest operating systems. Type 2, or hosted hypervisor, runs on the host OS. In this case, the guest operating system runs at the third level above the hardware. There are a number of underlying factors an automation engineer should take in consideration when it comes to selecting the type of hypervisors for the embedded system design. For optimal performance, automation engineers turn to bare metal hypervisors as it offers the least amount of system overhead. Moreover, bare metal hypervisors offer excellent system resource control, therefore allowing the user to better manage VM resources. Hosted hypervisors offer excellent hardware compatibility. They can be run either on Windows or Linux-based platforms, which are the two most widely used operating systems for embedded system applications today. However, hosted hypervisors do not offer real-time properties, making them not suitable for embedded applications. Hosted hypervisors provide ease of use. Installation can be done fairly quickly, and are relatively easy to use when compared to the bare metal variants. When reliability matters, embedded system designers typically turn to the bare metal hypervisor. Part of the reasoning here is that the bare metal hypervisors are used extensively in data centers and undergo rigorous conformance testing. Moreover, the lack of a host OS makes this option more appealing as it eliminates a potential point of failure in embedded system designs. Finally, when taking costs into consideration, system designers tend to consider hosted hypervisors as they are relatively inexpensive to implement versus the bare metal option. As you can see, there are a number of underlying factors an automation engineer must take in consideration when deciding which hypervisor to support for the embedded application. To summarize, a Type 1 bare metal hypervisor offers more security and reliable virtualized platform for embedded applications by limiting access of the hypervisor to only system administrators. By limiting access to software packages, Type 1 hypervisor vendors are better able to prevent malicious software from being introduced from the end users and user applications. So, what do AMD solutions offer for applications that require virtualization? AMD has enhanced virtualization capabilities by implementing hardware features in silicon. These set of hardware-assisted features, referred to as AMD V technology, contains on-chip features for virtualization to allow customers to better utilize virtualization resources with low latency, helping make embedded systems more safe, secure, and effective. Users can now encapsulate different tasks such as secure communication, data storage, and user interfaces in different virtual machines. For example, an instance of Windows 7 could be dedicated to run a user interface, while Linux runs secure communications and data storage applications. Virtualization enables each operating system to run completely isolated from one another, thus providing a mechanism to deliver high level of security and reliability for critical communications and data storage. Some of the features and benefits of using AMD V technology for embedded applications include virtualization extensions to x86 instruction sets. It enables software to efficiently create virtual machines so that multiple operating systems and their applications can be run simultaneously on the same processor. The second feature, tagged TLB, is a hardware feature in silicon that facilitates efficient switching between virtual machines for better application responsiveness and improved latency. The third aspect, rapid virtualization indexing, or RVI, helps accelerate the performance of many virtualized applications by enabling hardware-based virtual machine memory management. And finally, I/O virtualization enables direct device access by a virtual machine, bypassing the hypervisor for improved application performance and improved isolation of virtual machines for increased integrity and security. Finally, the real AMD advantage as it relates to virtualization is our scalability across our APUs and SoCs. We offer a complete lineup of footprint-compatible APUs and SoCs with AMD V technology enabled across our entire product stack, giving customers the freedom and flexibility to scale up or down the performance band and build truly virtualized solutions across the entire AMD product portfolio. Some of the reasons to integrate functions on the factory floor include to reduce system cost and power, lower installation and maintenance costs, support easy integration and deployment, and reduce user training time. In industrial applications, we are seeing operator panels being integrated with industrial PCs or PLCs. While these two solutions can be based on similar processing architectures, they have very different requirements for the software that runs on them. Operator panels predominantly use Windows operating systems to develop the user interface, while industrial PCs or PLCs utilize real-time operating systems to ensure reliable and responsive operations. To effectively integrate these two solutions, the integrated system must perform the functions of each just as well, if not better, than the individual platform. The key to achieving this is leverage virtualization technology to enable processors to run multiple independent and isolated operating systems on a single platform. This allows Windows to be utilized to develop a fully featured and immersive graphical user interface and a real-time operating system implemented to perform time and safety critical functions. The latest technology processors offer virtualization support in hardware to deliver efficiency and excellent performance for the developing software architecture. In industrial applications, automation panels are a type of industrial HMI system, largely used across factory floors for machine control and process automation. Automation panels are an operator panel that has real-time machine control functions integrated into it. This next example introduces cloud computing, an emerging trend gaining interest in factory automation. When it comes to cloud computing, virtualization offers three distinct characteristics, namely partitioning, isolation, and an encapsulation. Automation engineers can use partitioning as a means to support many applications and operating systems on a single platform. In this example use case, with the help of a hypervisor, a PLC utilizes a real-time operating system on CPU 0 to support secure, trusted, deterministic control of a machine or equipment on a plant floor, while running non-real-time operations on CPU 1 to facilitate transmission of data either wirelessly or via Ethernet to the cloud, which can be accessible later in time by a smart device or PDA. By partitioning each virtual machine, virtualization offers complete isolation for each subsystem. Through isolation, each machine is protected from crashes and/or viruses in the other machine. In this example use case, in the event CPU1 crashes and is unable to transmit data on factory operations to the cloud, the PLC is still able to operate deterministically on the plant floor, thus mitigating the need to shut down the entire machine for maintenance and supports, which would result in loss of productivity. In addition, the factory operator is able to service the isolated subsystem that went down without impacting real-time PLC operations to facilitate transmission of factory floor data. Finally, virtualization offers complete encapsulation when it comes to cloud computing. Encapsulation can protect each application so that it does not interfere with other applications. As an example for this use case, automation engineers could use the cloud to facilitate OS upgrades and timely software patch updates. It is possible new versions of operating systems could impact older software versions from functioning properly. A properly encapsulated system that has been placed in a virtual environment may continue to function as expected, thus allowing the plant floor operator to make the necessary OS or software patch updates to facilitate proper functioning on the plant floor. AMD has the industry experience of delivering solutions into the embedded space for over 20 years. At AMD, we recognize the long product lifecycle needs when it comes to embedded applications. As a result, the AMD Embedded Solutions Divisions offers a host of different product lines with 5+ years longevity, and in some instances, that longevity extends to as much as 10+ years. By providing a supply assurance program of 10 years on selected product lines, customers now have the flexibility and freedom to extend the embedded program life and, in process, recognize significant cost savings associated with frequent program refreshes. Some of the other benefits of the AMD embedded solutions for these applications include a broad software ecosystem with support for a variety of operating systems including Windows, open source Linux, and real-time operating systems. And to help shorten software development and debug time, tools are supported from a variety of vendors including Sage and Biosoft. The AMD APU and SoC solutions offer very good x86 performance and excellent graphics performance while remaining within the critical power envelopes of industrial PC applications to keep things operating reliably and power costs down. Support for hardware virtualization helps to facilitate platform integration by enabling multiple operating systems to operate independently on a single platform. And remote management helps to increase system reliability and reduce service costs through service alerts and remote diagnostics, and enables the deployment and tracking of firmware and software updates to help increase security. Finally, the architectural compatibility between AMD APUs and SoC product families makes it easier to leverage the same software solution across OEM product lines. The wide power and performance scalability in compatible footprints enables a single hardware design to serve multiple product categories. To summarize, when it comes to embedded applications, Virtualization offers a path to real-time performance alongside a mainstream operating system. Embedded systems stand to benefit from implementing virtualized environments as it enables automation engineers to build highly integrated, cost-effective system designs that are hardware and software scalable. With the machine-to-machine revolution taking place in factory automation, virtualization serves as the key to deliver a secure and reliable embedded system design. By leveraging AMD V, automation engineers stand to benefit from the hardware-assisted virtualization features implemented across the entire AMD APU and SoC product lines. Thank you for your time today in letting me speak to you about virtualization and its application in industrial control and automation. For more information on AMD embedded solutions for industrial control and automation applications, please visit www.amd.com/industrial.